All right, so let's start with discussions related to MOSFET. The first thing that we all know that transistors come in at least two varieties. One of them is the bipolar junction transistor, which we have been discussing in the last couple of lectures. The other one we know is the field effect transistor. And in field effect transistor also come in a lot of variety. And the one that we are going to focus on is metal oxide semiconductor field effect transistor here. A lot of slides here in this today's lecture would be familiar. They are from E210. So we'll gradually build up, warm up to this particular topic here. Okay. All right. So as I said, field effect transistors are a broad category of transistors. And there are MOSFETs, and among MOSFETs also we know that there are many varieties, and there are other kinds of field effect transistors also. For example, we had seen when we were looking at Schottky barrier diodes, we had seen a device called metal semiconductor MOSFET, right? So MOSFET was another kind of field effect transistor here. Just to remind you, when we are talking about transistor, one of the properties that we are looking at is that a transistor should exhibit a strong transconductance, meaning that the output current should be a strong function of input voltage and a weak function of the output voltage here. So we are looking for this property here, that del I0 by del Vn is much larger. Transconductance is much larger than output conductance here. We're looking for that particular property from this device, from this transistor here. All right. Okay, so let me remind you about the field effect principle. So if we have a piece of N-type semiconductor. We know that there are a lot of electrons in the N-type semiconductor, along with ionized dopant atoms here, denoted by positive charge here. So if you take this piece of N-type semiconductor, put two contacts, you apply a voltage here to the piece of semiconductor. We know that there are a lot of electrons. The electrons are going to flow into this particular contact. The current will flow from 5 to 0 here. So current will flow. Now the idea is in a transistor, now note that what we are looking for again, we're looking for a way to modulate the current. Let's say these are the two terminals here, right? We are looking for a way to modulate the output current through some another voltage here, right? So think about this current now flowing between these two terminals, and we want to modulate that current through a separate pair of terminals here, right? So what we could do is very simple principle. You could think of adding another plate. Think of it as a parallel plate capacitor, right? So this is one plate here. Think of the semiconductor as another plate here. In between, we have air right now. You can put a dielectric. So now once you have a capacitor, note that once you apply a negative voltage, then you'll put a negative charge here. And negative charge would require, as you have seen, what it would do is it would repel away the electrons from the surface. These electrons are the ones that have gone from here and traveled, and they're sitting over here on this particular plate here. So thereby, what you have done is you have taken a part of the surface and you have depleted it of electrons, right? So when you apply negative voltage, it repels all these electrons. The electrons go through the ground here and come and sit on this particular plate here, and this region becomes depleted. And now earlier, the current was flowing through this whole piece of semiconductor. Now it's flowing through a narrower part of the semiconductor here. A narrower part, so you can imagine that if the cross-sectional area becomes less, then my resistance is going to increase, and thereby the current flowing through this will alter. And therefore, we have what we call as field effect principle. By applying a field here, electric field, we have modulated charge here, and by modulating the charge here, the free charge here, we are modulating the current, right? So that's the modulation of conductivity using electric field is what we call as field effect principle. And we know that we can see here that a device will exhibit transconductance because a current is flowing between these pair of terminals here, and we are changing the current flowing between these pair of terminals by applying a voltage across a separate pair of terminals here, a separate terminal here, right? So the device is going to exhibit transconductance, and it's not showing necessarily that transconductance is larger than output conductance. For that, we have to do a little bit more work to see that, but at least is exhibiting this property of transconductance here. So the principle is very simple, as you can see. Is basically like a parallel plate capacitor, and using that you alter the charge in the semiconductor and thereby alter the current. And it's no wonder that this particular principle was realized very early. And you can see the first patent on a transistor filed in 1928 by this person called Lilienfeld, and he was not able to make it. The technology was not there at that particular time to realize it. But then, as I've said earlier, the Bell Labs team wanted to build a transistor like this only. Similar principle they wanted to build. They were not very successful. And in the process, they ended up inventing the point contact transistor and the junction transistor. All right. So what we have said is the field effect transistor is here. We can, we can't let a plate hang in the air like this here. So it's more convenient that all you need is in between a dielectric. So and in a silicon, the best dielectric is silicon dioxide itself. Okay. So thereby you can get a metal here, this plate gate here, oxide here, and you have a semiconductor here. So what you are seeing here is a field effect transistor, but based on metal oxide semiconductor. So it's a MOSFET. Okay. All right. Now the transistor that I just described is a transistor that we call as depletion mode transistor. The reason being was we said that what we have is, now I'm showing a better picture of the transistor. So we have oxide gate, we have a source now, and we have a drain. Source is N plus, so that we can make good contact to the semiconductor here. Similarly, drain is N plus, so we can make good contact. And in between, we have an N-type semiconductor, but we also have a P-type here. All right, and therefore, what you have is a channel already existing between source and drain. And now you would expect, even if you don't apply any gate voltage, you would know that between P and N-type, there is going to be a depletion region. So the whole N-type layer is not conducting. A part of the N-type layer will be depleted. But if the depletion layer is small enough, then you know that there would be a N-type layer with electrons present here. So there's a channel between the source and the drain. And if you apply a voltage, a current would flow. Now, the idea is, so if you apply 0 here, body 0 here, and 5 volt here, a current would flow. And so why it is called depletion mode? The idea is that there's already a channel. When you don't apply any gate voltage, say gate voltage is 0, current is flowing. And typically, you apply a gate voltage to deplete the channel here, to remove a part of the channel, as we just said. So this is shown more clearly here. So you apply -1 volt, you remove the electrons from here, and you put it on the gate. And so you have only this much part of the channel is left here. In this case, we are not showing, in fact, a more accurate diagram would have shown that there's a depletion region here also, at the bottom also. Okay, there's a depletion region here also, which is not shown here. And you apply -2 volt, well, you deplete more of the channel, and the current becomes even smaller. And eventually, of course, if you apply large enough, the entire channel is gone, and this is what we call as the pinch-off condition. So you can see here that this whole transistor is being operated on the basis of depletion. You already have a channel present, and then you apply a gate voltage, increasing gate voltage, to deplete the channel here. The transistor that is most commonly used is the enhancement mode transistor here. Okay, so we'll enhancement mode, and another one, a more perhaps appropriate name based on this operation, is an inversion mode transistor here. All right, so the structure is, you take P-type silicon. What you do is you oxidize this P-type silicon here. So a part of the silicon here is exposed to oxygen at high temperature, and the whole region is then converted into SiO2 here. So this is oxidized, and then on top you deposit a metal. Usually in the past, polysilicon was more common, polysilicon which was heavily doped. So it acts like a conductor, and metal is now more commonly used. So you have the structure here. Then you dope this particular region N plus and N plus here. You deposit metals here, say aluminum here. Because it's N plus, it forms good contacts here. And of course, you make the contacts here, right? So that's the structure. You have source, you have drain, you have gate, and you have a body here, which is so MOSFET is a 4-terminal structure. Source, gate, drain, and body over here. All right, so if we look at this particular structure, we can see that between the source and the drain, normally what we have is, we have a PN junction here. We have an N plus here and a P here. So you can see a PN junction with this direction shown here. And similarly, you have an N plus here and a P here with the direction shown over here. So you have 2 PN junctions between source and drain. And we call these back-to-back PN junctions here. And note that one PN junction will always be reverse biased. Right? So if you forget about the oxide and the gate and just look at this particular N plus, P and N plus, So it's two PN junctions back to back. One of them will always be reverse bias. So normally this between source and drain, I have very little current. Even if you apply a voltage to drain here, you get very little current depending on the leakage current of the one of the reverse bias diodes. All right, so we don't get any current here, and therefore we have to do something special to create current. And the special thing is that we have to create a channel here. We have to create a channel between the source and the drain, and the channel, of course, has to be N-type, right? So normally the region here is P. We have to convert it into N-type. We have to convert it into a region which is rich in electrons. We have to convert it into an N-like layer here, and that's why it gets the name inversion mode. Somehow we have to convert. Although the surface and all this region is P, we have to convert it to a electron-rich region here. Okay, so that's why the name inversion mode transistor here. All right. So again, what we are doing in this particular case, note that this is the picture. At a, let's say when you apply 0 volt, the region is full of holes and you have ionized acceptor atoms, and there's no channel between the source and the drain. You apply increasingly positive voltage. Now, when you apply positive voltage, what you're going to do is push away the holes from here, and the holes, positive voltage will push. The holes are going to go here, come out of the body, and eventually that positive charge is going to travel and come over the gate here, right? So positive charge will be at the gate and leaving behind the ionized acceptor atoms here. Okay, so that's what you're doing. And so initially what is happening is you've reduced the number of holes at the surface. All right, so you've sort of, you can say you've depleted this particular region. This region doesn't have holes anymore. Okay, depletion region is formed near the Si-SiO2 interface here. All right, now you apply even larger voltage here. Well, you're going to push away more of holes. You're going to deplete even larger part here. So more of holes here, depletion region will increase. But something then interesting, depletion width is increasing. But something interesting begins to happen, and that is this particular picture here, that N into P is Ni square. So as you're depleting the holes from the surface, as you're pushing away the holes from the surface, P is decreasing, but then N into P is Ni square, and what you are doing is simultaneously you are increasing N. So that's why you see that earlier you could hardly see any electrons, but as you deplete, you begin to see more and more electrons appearing. And the electrons are negatively charged, so of course most of them are going to be there at the surface here. Okay, so N into P is Ni square. So as you're depleting the surface, as you're depleting this particular region, the electron density is rising. And then we can imagine that if you apply a sufficiently large voltage, which we call a threshold voltage, the electron density at the surface becomes strong enough, and a significant current begins to flow between the source and the drain, and we say a strong channel is formed, and current then significant current begins to flow between source and drain here. So that's the phenomena that we are talking about. Initially, between the source and the drain, there's only a P region. It's like back-to-back diodes, very little current. You apply more and more positive bias here, you deplete the surface, you create more and more electrons. Eventually, a stage is reached where you have a strong channel and current starts to flow, right? And you create a sheet of electrons here, which we call as the inversion layer here. So the heart of MOSFET then is this Mos capacitor here, right? So earlier I was showing you a MOSFET structure with a source, drain, body, and gate and all that. Now I'm just showing a part of the MOSFET, which is what we call as a Mos capacitor. We have a metal oxide and you have a semiconductor. So that's the heart of the MOSFET. This is where what you're doing is by applying a gate voltage, you are modulating the conductivity and you are creating the channel here. So for the sake of discussion, let's assume that the doping in the bulk here, the doping in the semiconductor is 10 to the power 16, which means that the electrons, the holes that are there in this particular layer initially are 10 to the power 16. And the electrons are going to be Ni square over Na. We'll take Ni as 10 to the power 10 approximately. So N will be 10 to the power 4. So that's the situation. Let's say when we don't apply any gate voltage, we have a lot of holes 10 to the power 16, very few electrons 10 to the power 4, right? And N into P everywhere is equal to Ni square. We'll take that, including at the surface. At the surface also, Ns and P and S here. Also, denotes the S refers to the surface here. Surface meaning the interface of oxide and semiconductor. Okay, the surface of the semiconductor. So we know now that what we can do is, as we apply more and more gate voltage, we're reducing the P here at the surface. We're reducing P, pushing the holes away, and thereby we are increasing N. So this particular diagram, if you see, this is what is happening here. P at the surface initially, when you don't apply any gate voltage, let's say it's 10 to the power 16, the number of electrons is 10 power 4. The product is equal to Ni square, which is 10 power 20. Now, as you apply more and more positive voltage, you push the holes away from the surface, so you're decreasing the hole density, which is going from 10 power 16, 15, 14, steadily decreasing. And as this is steadily decreasing, the N is steadily increasing. And so what is happening is the surface is getting depleted of carriers. Electrons are anyway very small, so you can forget about it right now. You can see very few electrons. The holes are getting increasingly depleted here. Eventually, you come to a stage here. Note that at this particular stage, PS here becomes equal to Ni, and N also becomes equal to Ni. So you've gone from a p-type surface to an intrinsic surface, which is intrinsic. Electron concentration is equal to hole concentration. You apply even more gate voltage, you're going to decrease holes even more. And as you decrease holes even more, the electrons increase even more. And now in this case, we have inverted the surface. Electrons are more than the number of holes. But then note, both number of electrons and number of holes is very small. Although the electrons are larger than holes, I have inversion at the surface, but inversion is not strong. If you keep on applying higher and higher voltage, a stage comes when the electrons at the surface become 10 power 16, the same as the holes in the bulk here. Now we say the surface is strongly inverted. The electron density at the surface has reached the level of the doping level here, 10 power 16, and the holes have become 10 power 4, and then we say a strong inversion is occurred here. And this point is what we call as the threshold. The formation, the creation of a strong inversion condition where the electron density at the surface, 10 power 16, is equal to hole density in the bulk, or the doping level. That point, that gate voltage at which this occurs is what we call as the threshold voltage. Okay. If you apply even more, well, the electron density is going to increase even more. 10 power 17, 18, 19. So electron density at the surface of a MOSFET in strong inversion is very large. 10 power 19 or even higher. Okay. So you're applying a large voltage. This increases strongly. All right. So that's the principle. Surface carrier density can be changed from p-type to n-type, and we are creating inversion. All right. So this is the same thing depicted in the form of a diagram here. So steadily, PS starts from Na, and PS surface hole density, and you steadily decrease, and hole density then becomes smaller and smaller. Same time, N is increasing, becomes larger and larger. A stage comes when N becomes equal to Na. This is what we call as the VT, the threshold voltage. And then N becomes larger as you apply more voltage. Okay, so that's the qualitative operation of the Mos capacitor. Next, what we have to do is look at things in quantitatively. For example, we would like to calculate under what condition do I have flat band. Flat band meaning what? That, if I ground here, and normally, even if you apply 0 volt here, you don't have a flat band condition. Flat band meaning the electron density at the surface is same as electron density in the bulk. The bands are flat. So normally this is not the situation because the work function difference between the metal here and the semiconductor here. So you have to apply a voltage to create flat band condition. Okay, so let's look at that here. This is something that we have done earlier, which is the energy band diagram, which provides a clear picture of band bending and what is flat band voltage and all that. So let's look at that. Again, our example is metal, SiO2, and a p-type silicon, which is 10 power 16. So as usual, the band diagram that we draw, we say, well, imagine each one of them as separate. Metal, SiO2, 10 power, take them all apart. Draw the energy band diagram of each one of them separately. Right, so that is done by drawing the vacuum level. Metal is characterized by a work function. We'll take, let's say metal is aluminum. Work function is close to 4.3. Sorry, this is p-type. So we will not take n-type silicon. We'll take p-type silicon here. So semiconductor silicon, electron affinity is 4.05. Valence band is going to be 1.12 away, so that's 5.17. We are taking p-type, so Fermi energy is close to the valence band here. And the oxide is being modeled again like oxide is an amorphous. You could think of oxide as a very wide band gap amorphous semiconductor. We'll take this as electron affinity 1, and the band gap of the oxide is close to 9 eV. So this is at 10, right? For 10 power 16, so change that. If this is 10 power 16 p-type, then this EF minus the separation of EF from the valence band is about 0.180. All right, so this is before equilibrium. After equilibrium, we know that the Fermi level is going to be flat everywhere. So that's what we do. We draw constant Fermi energy, then we draw the interfaces. We have an interface here, we have an interface here. Then we draw, we know that far away from this particular interface, the semiconductor is going to be the same, everywhere. So we can easily, once we draw the Fermi energy, we can draw that EEV is going to be 0.18 away from here. We know EC here. So that we can draw easily. We can also draw the vacuum level here, because vacuum level, note, this 5 eV is the separation of the Fermi energy from the vacuum level here. So this is the vacuum level here, vacuum level here. This one we know is 4.3 eV, so we can draw the vacuum level here. And we know that if you look at this particular picture here, Fermi energy here is higher as compared to this. So electrons are going to transfer from the metal to the semiconductor. You may wonder, well, if I have an SiO2, how are they going to transfer? Well, we are assuming that, SiO2, even though it's an insulator, will allow charge to flow through. When we talk about equilibrium, we're talking about long enough time, right? So it will allow some charge to flow through. Otherwise, also, typically what we have is, this is ground and the semiconductor is also ground. So there's another path for the charge to flow. So we assume that equilibrium has taken place. Electron has fallen from the metal and gone to the semiconductor here. So this has become positively charged. This is what we are seeing here. We can clearly see E naught is below E naught over here. So positively charged. So it's all going to bend like this here. It's going to go like this here from higher to lower in a continuous manner. Okay. How it goes is something that we have to solve Poisson's equation to determine. So this goes like this here. So all of them will follow. ECEV will follow here. And once we know this, note that the vacuum level is continuous, but the slope of the vacuum level denotes electric field. The electric field may not be continuous because the dielectric constant here and dielectric constants here are different. Okay, so electric field may not be continuous, but the vacuum level is continuous, and we can draw, and we end up with a diagram like this. Now, this is the diagram. So we can see here that even though we have not applied any voltage, EF is flat, gate to source voltage, gate to body voltage is 0. We see that there's a band bending, and this is what we call as the internal voltage. We can see here the metal here, the vacuum level is lower as compared to this, which means that this is at a higher potential. This is at a higher potential compared to this, and how much? Well, psi ms, psi metal, voltage of the metal minus the voltage of the semiconductor here is equal to phi s minus phi m, and phi s is here, one can note, phi s is 5 eV, and phi m is 4.3 eV, so psi ms is equal to 0.7 eV. So there's already an internal voltage present inside my system because of work function differences. And I have to apply a voltage to create flat band. See, the bands are all bending here, already bending here. So I have to apply a voltage to create flat band. And what do I have to apply? Apply a voltage opposite to this. So my flat band voltage is going to be, note, flat band voltage is going to be minus of this value, phi s minus phi m by q, which can be written as phi ms by q, which is equal to, this is equal to minus 0.7 volt. So my system has a flat band voltage of minus 0.7 volt. If I don't apply any gate voltage, I have an internal voltage of 0.7. I have to apply a minus 0.7 to create a flat band condition. Okay, so this is what I was talking about, that even if you don't apply any gate voltage, there's already band bending because of work function differences, and I have to apply this much condition to create flat band here. So one can see clearly then how to determine the flatband voltage. It's simply equal to the difference in the work function of the metal and the work function of the semiconductor, right? So in this case, 4.3 here is the work function of the metal, 5 is the work function of the semiconductor, and so flatband is negative. All right. Now, as I said, what we want to do is gradually progress to doing a more quantitative analysis of our Mos capacitor here. So this is the condition that I've shown here in flatband, right? You can see here. If you apply a gate voltage equal to flatband voltage, this is what would happen. All the bands are flat, right? Now, let's have some couple of definitions. Psi potential anywhere in my semiconductor, we know, is minus EI by Q. You can define it in many ways. Psi can be equal to minus EC by Q or minus EV by Q minus E naught by Q. Yeah. Which one? Okay. So what you're saying is I've applied a voltage, and how come the Fermi level in this case is flat here? Now note, I was waiting. Why were people not asking? For example, I was saying that I've applied a voltage, and I was saying N into P equal to Ni square, right? Why am I saying those are equilibrium conditions, right? N into P, Ni square, right? So this is a system. If you look at it, metal oxide semiconductor, right? So in this system, we don't have any current flowing, right? Everybody agrees. As I go from this region in steady state, if you are transient condition, of course, capacitor gets charged and discharged, you have current flowing. But in steady state, I don't have any current flowing. Now, if I don't have any current flowing, all of you know that Jn we had written as N mu n, right? People remember this? Jn is N mu n dfn by dx. What does it mean? If I have no electron current, Fn is 0, flat everywhere. Same I can write, Jp is P mu p dft by dx. I don't have any current. Whole quasi-Fermi level is flat everywhere, right? So that you agree that electron quasi-Fermi level and whole quasi-Fermi levels will be flat. Why will they differ? This equation also people remember, Np equal to Ni square e to the power Efn dfp by kT, right? I don't have any external excitation or anything, so I don't have Np, and I'm not injecting anything, so I don't have Np, Efn. I don't have this particular condition there. So Efn is flat, EFP is flat, and both are equal. Okay, both are equal, and so we still, strictly speaking, yes, I don't have equilibrium, but Efn is same as EFP, and both are flat. So we continue to denote this particular quantity here, Efn. So it's as if my p-type layer remains under equilibrium. No currents are flowing. Okay. So psi, we know, can be written as minus EI by Q plus constant. Potential can be defined in many different ways. Okay, in terms of intrinsic level, in terms of valence band, conduction band, E naught, these are all the same ways. The only thing that changes is your reference level. And at various times, we choose different reference levels to, for convenience sake. So in this case, psi is minus EI by Q plus constant, and the reference that I'm going to choose is EIB by Q. EIB is what? The intrinsic level in the bulk. Note that this is the surface here, and in the bulk meaning far away from the surface. EIB by Q is what I'm choosing as a constant, because when you go far away, the intrinsic level is going to be there where it is, nothing is going to change. All right. So we are taking this as a reference level. Okay. With this thing in mind, so psi x, we are going to write psi x is in this direction here. So psi everywhere is going to be minus EI by Q, same, and constant is EI by Q. Okay, so that's the constant. I can choose any constant that I want. So that is up to me. So with this definition, now if I apply this definition to this band diagram, what do I find? Psi EI is everywhere the same. So what does it show? That everywhere psi is 0. Everywhere psi is 0. Psi s is 0. Psi in the bulk, B denotes bulk, far away from the surface. So psi bulk is 0. Psi s is 0. Bands are flat. EI is equal to EIB. So that's the definition that we'll use for potential. Okay, everywhere potential is going to be measured with the intrinsic level in the bulk as a reference. Now, with n equal to Ni exponent EF minus EI by KT, this is an equation that we know. Now, with this definition of psi is EIX minus EIB, you can easily, through a two-step algebra, show that n equal to Ni square over Na exponent Q psi by KT. Similarly, P equal to Ni exponent EI minus EF by KT we know. And again, with one or two steps of calculation, you can show P equal to Na exponent minus Q psi by KT. So what it is saying is, this is how we are defining psi. And once you know psi, well, you can express n in terms of psi and you can express P in terms of psi. And it makes sense. You can see here, we said psi is 0 everywhere. So you put 0 here. N equal to what? Ni square over Na, which is what we know. The number of electrons in this p-type layer has to be Ni square over Na. What is P? P is equal to Na. Bands are flat. Everywhere is the same hole density. So you can check that this makes sense. P equal to Na, N equal to Ni square over Na. All right. So these are the definitions. Keep in mind. Okay. Let's look at this condition here. I'm only showing a part of the diagram. I'm not showing SiO2. I'm showing what happens to band bending here. What is happening now? This condition. What is the psi s? Okay, so before that, let's calculate this value here. How much is this value here? Q phi f. How do I calculate? Well, P equal to Na, right? P equal to Na. In this equation, we know P equal to Ni exponent Ei minus Ef by KT. And we know that P equal to Na in the bulk. And in the bulk, it is EIB minus EF by KT here, which is nothing but this term here. So from here, we get this phi f is equal to KT by Q ln Na by Ni. All right, so this is what it is. You know, in Mos capacitors, we frequently use this particular symbol, phi f, to denote the separation of the intrinsic level from the Fermi energy in the bulk here. And that's phi f is KT by Q ln Na by Ni. So now, what is the surface potential here? Can everybody see that psi s equal to phi f? How do you measure psi? Psi is measured from where? Note again, keep that in mind. Psi is the position of EI measured from the bulk. The position of EI measured from the bulk, right? So now, position of EI at the surface. If you're looking at psi at the surface, it's EI at the surface, measured from the bulk. So how much is this from this distance? Nothing but phi f. So this denotes psi s equal to phi f. What is the electron density at the surface? Well, even without looking at it, you can see what will be the electron density. This is Fermi energy, note. Fermi energy, EI. EI is coinciding with the Fermi energy. So it's equal to Ni. And you can see here, Ns equal to Ni square over Na. This is a formula. Exponent Q psi s by KT. If you take psi s equal to phi f, plug it here, you can work it out that Ns equal to Ni. Similarly, Ps is equal to Na exponent minus Q psi s by KT. Put here psi s equal to phi f here and work it out, you'll see Ps equal to Ni. So this is what is happening under this condition here, when I draw a diagram like this. Okay. Now this is the diagram where what I'm doing is, note the hole density at the surface has become very small, Ni. Earlier the hole density was equal to Na, now it has become Ni, so hole density has become small. So I'm depleting the surface here. So this is the depletion condition here. Okay. Depletion condition is when I'm above flat band. See, at gate, this condition you can clearly see that I have to apply a gate voltage to pull the bands down. I have to apply a gate voltage which is positive over and above the flat band voltage. Go back here. I have to apply a gate voltage equal to flat band to create this condition. Now to pull the bands down, I have to apply a further positive voltage here. So that's why we are saying VGS equal to, VG has to be greater than flat band, but VG has to be less than threshold voltage, because threshold voltage is when I have strong inversion here. So depletion condition is this: VG greater than V flat band, VG less than threshold. All right. Let's see if you can draw this one here. Draw the energy band diagram when Ns equal to PB. PB refers to bulk. Ns equal to Na. Can you draw the energy diagram for that? Only in this part of the semiconductor. How will the energy diagram look like? When so Ns equal to Na. Ns equal to Na. Draw the energy diagram and use this as a help. Use these equations as a help here. How will the energy band diagram look like? And Ns equal to Na is what condition? Electron density at the surface has become equal to Na. So that's the condition for threshold. Okay, so this is very important. This is the condition for threshold voltage. At threshold, I have this one. Ns equal to Na. So let's draw the energy diagram quickly. So also please find out what is psi s. What is psi s equal to? When you create this condition, what is the surface potential? Psi s is potential at the surface. Note that all you have to do is, this is the expression for Ns. Ns is equal to Na. Find out what is psi s and draw the diagram. So put Ns equal to Na here, and psi s comes out to be twice of phi f. Psi s comes out to be twice of phi f. So when psi s is equal to 2 phi f here, then you are creating this threshold condition here. Electron density at the surface is equal to the background doping. How will the band diagram look like? Band diagram will look like agreed? Everybody is getting this? This is how band diagram will look like. How much is this? So this separation is how much? Phi f. And how much is this from here to here? Another phi f. So this is phi f and this is phi f here. Total band bending that you can see here is 2 phi f. Okay. So we know how much band bending we have to do to cause the inversion to occur at the surface here. Psi s equal to 2 phi f. What is psi b equal to? Bulk potential is how much? Psi b equal to, according to our definition, 0. So how much is the total drop in the semiconductor as you go from here to here? Voltage drop in the semiconductor? Psi s minus psi b, which is nothing but psi s. So you have to create that much potential drop in your semiconductor to create the threshold condition. All right. Now, can you draw the condition for accumulation, where you are accumulating holes at the surface? This is not, right now what we said was Ns equal to Na. Can you draw a condition where Es is equal to, let's say, 10 Na? Es is equal to 10 Na. Can you draw the energy band diagram and find out what is the surface potential and all of that? Psi s equal to, so draw the energy band diagram, find the surface potential. When you have hole density at the surface which is 10 times Na, what have you done? You've accumulated holes at the surface. Normally holes are equal to Na. Now you have created at the surface hole density which is 10 times higher. Right? So that's accumulation. So can we draw the diagram for accumulation? Find out what is the surface potential. So what you should develop is an ability to, for various conditions, draw an energy band diagram, find out what is the surface potential under different conditions. Flat band, which is obvious, depletion, inversion, uh, accumulation, all of that you should be able to do using basically this set of equations that you see. So note that P is now 10 times Na, which means psi will become negative. Psi will become negative, which means now bands are going to bend up. Bands are going to bend up. By how much will they bend up? Well, how do you calculate? Well, basically you calculate from here. P you put equal to 10 Na. You put 10 Na and then you calculate what is psi. So by how much will psi bend? That will be equal to, psi s will be equal to KT by Q. And then 10. That's it. That's the amount of band bending that you have to cause at the surface to create accumulation. So what we are seeing here is that you can create accumulation, depletion, inversion, any of that, and we can find out what is the surface potential under each condition. Okay, now the next thing is surface potential is what? It is telling you. So let's go here, depletion, all of that we have seen. Strong inversion also we have seen. So this picture is also clear. Look at that. Flat band. How much voltage do I have to apply to cause flat band? VGS equal to V flat band. Right? This we've already seen. Okay. How much voltage, gate voltage do I have to apply to cause this to occur? Remember what you just found out? We found out what is the surface potential. Surface potential here and potential in the bulk is how much? 0. So we know how much is the drop here. Now we are asking how much gate voltage do I have to apply to create this condition? Well, look at this. Does it make sense, this diagram? First of all, what do? I create a flat band. How much voltage do I have to apply? VGS equal to V flat band. Then on top of flat band, I have to apply extra voltage to bend the bands down. Right? Extra voltage I have to apply. That extra voltage, where is it going to drop? VGS, you're applying the voltage between here and here. That extra voltage, some of it is going to drop here and some of it is going to drop here. And that's why you have any voltage that you apply more than the flat band creates band bending. Either accumulation or inversion or whatever. So VGS minus V flat band equal to that extra voltage. Some is dropped here, which we call as V oxide, and some is dropped here. What is dropped in the semiconductor? We've already seen is psi s. Right? How much is dropped in the oxide? How do we find that out? Okay. So any doubts regarding this equation? VGS equal to flat band. When VGS is equal to flat band, what is Vox? What is psi s? 0. Bands are flat, psi s is 0. And when bands are flat, there's no electric field. And if there's no electric field in the semiconductor, no electric field in the oxide. So Vox is 0, psi s is 0. Now you apply something extra than the flat band voltage. Now there's a band bending here and there is a drop in the oxide here. How do I calculate the drop in the oxide? Well, it's obvious. If I know the electric field in the oxide, I can write V oxide is E oxide into T oxide. That's not a problem. Now, is this also obvious? Look at this equation. When you create band bending, you always create charge. This is the charge, let's say, in the semiconductor. What is this equation? Gauss's law. Gauss's law applied where? At this interface. What is the electric field going? E oxide. So dielectric constant multiplied by E oxide. Look at the direction. Electric field is going into the surface. And what is the electric field at this point? As you go into the bulk, there are no charges, no electric field. So electric field is 0 here. So can everybody see that this is nothing but application of Gauss's law at this particular point here. So now what you're seeing here is minus E oxide is equal to QS. So how do I find the oxide drop? Oxide drop is going to be E oxide times T oxide. E oxide is related to QS. Now, will QS be related to psi s? QS is what? Charge here. It's related to psi s. So all we have to do now is solve Poisson's equation, which will relate QS to psi s here. And we'll get one single equation which you solve, to determine how much is QS, how much is psi s for any value of gate to source voltage that we know. Okay? So that's the only thing which is left here, relationship between QS and psi s. Okay, we'll do that in the next lecture and then build a model for threshold voltage.